Good morning, one and all, and welcome to another episode of Finzics. It's Mr. Finn coming at you from neighborly Northville. Yesterday, guys, we were talking about the concept of terminal voltage and internal resistance. So I hope you got a chance to look that over. It can be a little tricky, but as long as you know how to measure those voltage drops, remember just taking the voltmeter on both sides of the resistor, and that will give you the applied voltage. Today I got to talk to you about the most complicated concept in the whole section, Kirchoff's laws. Well, actually, the concepts are not that complicated, but the applications can be a little bit tricky. So, I'm going to walk through these with you today, go through an example, give you a chance to practice, and then, of course, I'm available for the Google Meets on Thursdays. And, of course, if you have any questions, you can fire them in to the email, and I'll try to address them on the future video casts. Okay, guys, Kirchoff's laws. Let's take a look at an example of what we have here. Okay, guys, there's only two real rules for Kirchoff's laws. Now, why do we need this if we have such a huge advantage with resistor reduction? In other words, combining resistors in parallel or combining resistors in series versus the ways that we do that to break it down to one simple circuit. Well, that would be great. And we can use resistor reduction a lot. But what happens when you have a voltage supply up here, a middle branch right here, and another voltage supply on the bottom? What do you do if you have two voltage supplies? Well, it becomes complicated because you would have a current, we'll call it I1, the blue current, out of the 4-volt supply going through a resistor here. And then you have a junction here. We'll call it point A, point B over here. You have a junction. Feeding that junction from the bottom, we think, is a 2-volt supply and a 1 ohm resistor here. I labeled that purple current as I2. So I've got I1 and I2, the I1 on top and the I2 on the bottom. Going into point A, I have I3 coming out of point A, and that's in pink. Now, how do I know the directions of the currents? I really don't. I'm just going by what I think is going to happen. In other words, the front of this battery pushes charge energy through the electric field according to its positive value. The same thing for this one. Well, it could be that this current is actually charging this battery. So the current would flow the opposite way. It doesn't matter what that happens. Just set it up the way you think it's going to run. And if you're wrong, the currents will come out negative in the answers. And then you'll know that you drew them the incorrect way. But don't flip it until you get to all the way to the end of the problem. And then just recognize that your currents were backwards. Okay, guys, here are the two rules. Number one, the current flowing into any junction will be the same as the current flowing out of any junction. We're going to use A as our junction. So the two currents that flow in are I1 from the top and I2 from the bottom. So I1 plus I2 flow into the junction. What's flowing out of the junction is I3. Now, how come the current has to be the same flowing in as flowing out? It's a great question. Remember, guys, charge cannot build up on the middle of a conductor. That's impossible. That would be a capacitor. So charge flows through a conductor. It can't stop in the middle and build up. So therefore, charge flowing into point A must equal charge flowing out of point A. The second rule, the sum of all the voltage drops around any closed loop must equal 0. Now, this stems from the stuff we were doing the other day. But if I take this voltage supply and I drop the voltage across R1 and the voltage across R2, I should get back to the back of the battery again. And according to terminal voltage issues, if we ignore the internal resistance, we're simply going to get the total voltage drop of 4 volts. If there was any voltage left at the back of the battery, we wouldn't have a 4-volt difference. And the same is true of this voltage supply. So really, Kirchoff's laws are actually very simple. but it's the application of them that can get complicated very quickly. On this diagram, we have three unknowns. Therefore, we must need three equations at the very minimum to be able to solve. Let's solve the two loops first. Let's take a loop equation for this loop up top, moving in the clockwise direction. 4 volts minus the current through the 1 ohm resistor, and that's I1. So minus I1 times 1 ohm. Then, in order to get back to the back of this battery, we're going to travel through the resistor 1 ohm that's in the I3 branch. Therefore, dropping another voltage, I3 times 1 ohm. So my whole first equation is 4 volts minus 1 I1 minus 1 I3. If I take another loop around this bottom loop right there, again, moving this time in a counterclockwise direction to make sure that I'm still with the front of the battery. In other words, the positive part of the battery would dictate a counterclockwise direction. Loop 2 would be 2 volts minus I2 times the 1 ohm minus, again, I3 times the 1 ohm. And that would equal 0. Because again, sum of the voltage drops must equal 0 around any closed loop. The only thing left, guys, is that junction. Therefore, I3, which is the middle branch, that's leaving the junction A, I1 plus I2 must equal I3. So there we have it. Those are our three equations for Kirchoff's laws. Now, you may be asking yourself, what does this do for us? Well, since we have this junction in terms of I3, I can sub this equation into each of those and break it down to two equations and two unknowns. I'll walk through that with you real quick here on the next board. Okay, guys, let's take that next board here and see what's going on. Our number 1 loop, that's the loop up here. 4 minus I1 minus I3 will equal to 0. Well, I3 was I1 plus I2. So I just substituted I1 plus I2 for I3. Remember, it's a quantity substitution. Therefore, I've got minus, which would then be distributed to both terms. And that's how I get 4 minus 2I2 minus I2 equals 0. The next loop is the bottom loop. 2 minus I2 minus I3. Well, again, that's quantity I1 plus I2. So that boils down to 2 minus 2I2 minus I1 equals 0. Now I have those two equations, and I substituted I3 into both to eliminate I3. So what's next? Well, we're just going to multiply one equation, or we could substitute it. That would be fine. I'm going to multiply this equation by the value of minus 2. Why would I do that? Because I can get minus 8 here. That's my voltage. I'm going to take negative 2 times negative 2 to get plus 4I1. Negative 2 times a minus I2 to get plus 2I2. Then I'm going to take that equation and bring it right down here and add it to my second loop. So 2 plus a negative 8 is a negative 6. Negative 2I2 plus a 2I2 is a 0. And negative I1 plus a 4I1 is a 3I1. Clearly, that's going to come down to 6 equals 3I1, or I1 equals 2 amps. We can then take that equation and move it back up into the others to find the remaining pieces. There's a couple of examples like this in your book, guys, and I would recommend going through them very, very carefully. You can write the Kirchoff's laws correctly and do some very simple algebra mistakes to get those answers wrong. Or, a lot of times, students start to realize they've drawn something incorrectly, and then in the middle of the problem, they try and switch it again. Don't do that. Whatever you've drawn here, write the equations the way the arrows have been going. And if your current goes through a resistor, that's a voltage drop. So that's a minus a voltage drop. But if you came across a voltage supply, or you went against the current direction, that would be called a voltage add. And instead of dropping a voltage drop, you'd be adding a voltage drop. It would be a voltage add. So just follow the conventions of the current that you've drawn, drop where it's appropriate to drop, or add where it's appropriate to add if you're going against your current. Look it over, guys, and I'm sure you'll have questions. And we'll do a couple of these on the Google Meet when we get together. Okay? Let's wrap up today. Okay, guys, no doubt Kirchoff's laws can be tricky, but just set it up the way you know how. Be disciplined about it. And don't forget to distribute those negatives. That's one of the key places where a lot of students make mistakes. We'll try to keep our Kirchoff's laws applications simple enough. But go through the ones you have in the sections. I think figure 1931 is one of those that does a really nice job of describing, as they move through that example, just how this works. Okay, guys, we'll be back on combination circuits for a couple days, and we'll wrap out the whole unit at the end of that. Good luck, and we'll see you next time.